program to mitigate for the impacts of Columbia River dams on ESA listed fish. Sort of bottom line. So the goal is to help those ESA listed salmon and other fish recover by understanding, conserving, and restoring ecosystems in the lower Columbia River estuary. And the how of the restoration goal is typically floodplain reconnection or the enhancement of existing shallow water habitat, as well as the establishment of native vegetation communities, including removal of invasives. So the program has a formal adaptive management framework, as many of you are well aware. It's evolved over time. The key principles are listed here. You can dive into those later, but really it's all about engagement of partners, engagement of stakeholders, seeking lessons learned, capturing that institutional knowledge and learning, making the program better, every year as best we can. The three main components of that framework are learning, restoration, and monitoring. Starting with learning, that's what we're doing today. We're here as part of, other science seminars as well. You'll hear a lot about the synthesis memorandums and in particular SM3, which was just recently held. There's a master matrix of learning. There's pre-construction site visits, periodic post-construction site visits with experts and folks in the program to, again, assess performance, understand, what we could do better, document that, and kind of, again, each year making the program better and our project implementation more effective. Strategy for restoration continues to emphasize, obviously large-scale, full hydrologic reconnection. Near the main stem is, of course, the goal. It's harder and harder each year to find those large projects. You don't often find a Steigerwald, and it takes, many, many years to make those happen. So smaller projects are also pursued with an emphasis on the impact from a sort of landscape scale perspective. The program has continued to develop what's called the implementation forecaster, which if you don't know, you'll hear a lot about that in the program for those new folks. It's a really, really great tool that the program has to identify and screen potential project locations based on user-defined criteria. The program also engages a group that's known as the Expert Regional Technical Group, the ERTIG. Some of the members are on the call today, and you'll hear more about them. But bottom line is, they review projects, assess benefits of projects, and then provide sort of their scientific expertise across various fields to the program managers and the program at large, again, to learn, to do the science that we need to better understand and better implement projects. So the monitoring is obviously an essential part of the program. Traditionally, CEERP's been organized into, the monitoring has been organized into the four categories you see here. If you're curious, and for those newbies, CB Fish website is a great resource for the program's monitoring reports historically. As we begin to move into the third decade of CEERP, as we're talking today and as we talked about at SM3, there's a fair bit of discussion about how the monitoring aspect of the program should best evolve, things to do more of, things to do less of, how to do it differently to better meet the needs of the program. So who is CEERP? Bonneville is obviously part of CEERP. They're one of the two action agencies that work in the estuary. They continue to fund the majority of the restoration work in the ground. They have a lot of flexibility in funding, much more than the Corps does. So Bonneville funds, again, the vast majority of project implementation. They have a member or two actually are now on the steering committee for the ERTIG, so sort of help guide the steering committee to dig into and answer those questions that we think as program managers in the program need to have answered to better manage the program. So the Corps' role as dam owner and operator is sort of to balance all of those sometimes competing purposes. We've got to maintain the navigation channel, we've got to provide for the hydropower, and all the while try to do the ecosystem restoration in the estuary. We do have a specific authorities with which we can use to implement projects. They require cost-shared partners, but typically what the Corps brings to the estuary program is funding for the scientific research that happens And so a lot of the AFEP studies, you'll hear about those today. Those are funded by the Corps. Of course, NOAA is a part of the program. They're the regulator. They do a lot of good scientific work, contributing to our scientific body of knowledge. And they're also a member of the ERTIC Steering Committee. And of course, our partners, they're the ones out in the mud and muck, counting fish, counting bugs. They take BPA and core funding and turn it into projects. So thanks to all the folks who are on the call today and out there doing the hard work, cold, wet work to actually get projects in the ground and complete our studies. So in terms of when, we just want to do a quick overview of the timeline. Obviously in 2000, the Jeopardy opinion sort of kicked the program off. There was the ruling or the opinion that the hydropower system overall was going to endanger or likely to endanger the survival of numerous ESA listed fish species, and included as an RPA, among other things, upriver, that habitat restoration in the estuary should be done. And so the BPA, as a result, and the Corps committed to restoring at that time 10,000 acres of habitat. That was sort of the first goal. And then from there, there's just a few of the milestones that I thought were interesting for this group here. There's just a long history. We've got so much has gone on and so many studies, and again, dozens of projects. But this is just some of the stuff that I thought would interest this group. Over time, it's developed a sort of a formal ecosystem-based restoration plan. In 2003, LSEP was contracted as a restoration sponsor and partner. CLT, CREST, WDFW contracted in 2010 as restoration partners. Again, help getting those projects in the ground, help doing that monitoring work that is so important. That ERTIG, that expert group, was formed in 2008, and we've been, using them ever since to advance the program. And then there's the 3 synthesis memoranda that you see there: 2008, 2012, and then now in 2012, 2018, and 2025. We'll talk more about the 2025 SM3, but really what these are an attempt to synthesize and evaluate results from project implementation. So this is a critical element of CEERP's adaptive management process. It acknowledges new scientific findings, affirms what's going well and why, identifies need for improvement, and informs any adjustments to the future program's strategy and actions. I guess bottom line is, they're a chance to take stock of what's been learned and to help inform restoration and research decisions going forward. So it's really critical to what we do. Since 2004, the program's implemented more than 80 projects and reconnected over 11,000 acres of floodplain habitat. What's next? Quickly want to hit this. There's a lot of good stuff going on right now. The Corps is interested in the beneficial use of dredge material, looking at opportunities to use what's taken from the NAV channel maintenance program to maybe create shallow water habitat, to improve the way we do that, to increase the benefits and certainty that placing material in strategic locations can produce benefits. And so Chanda, who's on the call today and can answer questions later about that, is working on holding some workshops, getting stakeholder feedback, and then working on modeling how we can best use dredge material as shallow water habitat to maximize benefits to salmonids in the estuary. As it does periodically, as you heard, the ERTIC's working on 2 important technical products. One that Amy mentioned, the climate resiliency in the estuary, is out for regional review. If you don't have that, we can get that to you. And then there's also one in the works on conceptual foundation for CEERP, which is going to come out in the next month or 2. That's, I believe, turning into a journal article sometime later, but a really important sort of assessment of the program at all, and sort of laying the foundation for how we move forward, considering what's happening both in the estuary and upriver. Exciting news, we've also got a CEERP website in the works. It will not replace CB Fish. That'll still exist and have its own utility. but we are going to have a more informational hub highlighting what's been done, what we've learned, how we got here, where we're going, and why. And we expect that to be live in spring, summer 2025. Long coming for that one. And then we've got 2 studies planned this year that have gone through the AFIP review process. One is focused on prey exports, and one is focused on tracking the movement of juvenile salmon through the estuary. We've also got SM3 underway, as you know. SM3 is a little different this year, this go around. The last 2 were synthesis reports. They're out there. They're awesome. Great to be shared. They'll be on the website when we get up and running. This one, as you'll hear, we held a workshop back in, June. And there's a summary report that's out there. Most of you should have that. If you don't, we'll get it to you. But we're turning, or PNNL, working with, the rest of the program, is turning the SM3 into a journal article targeted for 2025. So many of you were at the workshop. PNNL put together a really great collaborative and engaging workshop over the course of 2 days, representing many organizations. Workshop had 6 sessions. There was the first session was the state of the science. Each of the 4 domain groups that were sort of self-selected tried to capture some of the key knowledge of the estuary specific to that domain. I'm not going to read through these, but they're in the summary reports. You can read them at your leisure. The second session was identifying critical knowledge gaps. The third, folks got a chance to exercise their right brain a little bit, and a fun activity to explain people's hopes and visions for the future of the estuary. That was really cool, and for better or for worse, all of the drawings are in that workshop report. We then focused on various monitored indicators, trying to understand the relationship between level of knowledge of a particular indicator and the importance of that indicator in the estuary. Then there was some time for self-reflection on an individual basis about what was learned, what we know, and then finally, as we'll talk more today, is wrapping up about research priorities. The group was asked to rank the various research questions that had been developed during the workshop, and then it was a really cool exercise to vote anonymously via phone or computer, and the results look something like this. So, clear consensus, you had those top, I think, what was it, 5 or 6, Catherine, that you have, but this is the full results, again, in the workshop report, but there was a clear consensus that, climate change, sea level rise, resiliency, adaptability of the estuary, what we need to know, what we need to do, were clear themes and clear research question priorities for the group. Besides what you see here, some of the broader takeaways from the group included that there's a vast amount of data that exists that we can use, but also there's a lot more data that we need to answer these questions. And then the final takeaway was how awesome it was to be there as a group, as you all know in person today, and I've heard. It was great to have everyone there. We got to walk around. We got to have happy hours. We got to collaborate. It was a great group. Great to be there in person. A really rewarding workshop that we're going to do more of going forward. So with that, take any questions.
Any questions for Mark? Anything? Anybody on Teams? Any questions for Mark?
I have a quick question. Sorry. Are we gonna that last slide that had all the research questions in the really small text? Are you gonna be able to share out this presentation, or would you be willing to share the presentation?
For sure. Presentation will be shared, but also, Laura, those are in the summary report that's been shared out.
Okay.
Did you get the summary report? I think you sent it yesterday. Okay, all right.
Maybe.
It does have the same list of questions.
Okay.
I have a question. I was wondering about, you talked about they're working on a study tagging and tracking salmon through the estuary. Is that new upcoming work, or is that like a continuation? Do you already have those data?
We are taking advantage of the tagging effort that's happening up by McNary. And so what we're doing is that's, a big effort, lots of groups are involved in that. And then so what we're doing is we thought, hey, we have a lot of questions about how fish move through the estuary, how long they stay, where they go, what sites they visit. And so we thought we'd take advantage of that by conducting a study, putting acoustic receivers out in strategic locations. And so we're working with USGS right now to finalize the scope and scale of that, where they're going to be placed. And that's the effort that it's for now. It's planned for a year, could be multi-year depending on the results that we get and how much we learn. If we need more, then we may continue that study. And yeah, Chanda, please chime in.
Yeah, we should just emphasize that we're taking advantage and leveraging data from that study, which is targeting yearlings, which are typically, I think the general assumption is that they're just flowing through and not really taking advantage of some of the habitat and site channels, et cetera, like the younger juveniles would. But there's a possibility from some of the individual-based modeling that's been done and some recent work by some of the Erdic scientists, and Kyle Tidwell is kind of expanding on that some certain small percentage of fish might actually kind of explore other areas. And so we don't know how much detection we're going to get, which is why it's only a year, to see of the percentage of fish that aren't just staying in the main channel and kind of blowing out. How long are they kind of taking advantage of some of those areas where there's been a lot of restoration and reach feed? So that's the caveat of, yeah, it'll be great if all the fish don't blow through and bypass and we get some detection, because I think we might have 400 by the time there might be about 400 fish that we could potentially detect by the time they get to the area where we're targeting with USGS. So more to come.
Thank you.
Thanks.
Is that through pit tags or is it through, and did you say only in Reach B or just that's where we're mainly interested?
Well, right now that's where the scope of this quote study, we only have resources to support like 3, I think, receivers. And this is getting into Mark's territory.
Or three sites. Could be multiple
sites.
receivers. Yeah.
Thanks. And so we're hoping to get a good level of detection in that lower area. But like I said, depending on the results of that first year, we talked to USGS and we can move receivers to get better detection in a subsequent year if it looks like, like maybe we got a lot of hit on one, but there's uncertainty about where they went afterwards. So we can move things around in a second or third year.
And they're pit arrays, is that right? Pit tags?
Yeah. No, acoustic.
No, acoustic.
Okay.
Yeah.
And then one more follow-up question. Oh, sorry, somebody else can go ahead.
Carrie?
Do you know, Mark, if this is the JSATS tags and that's why they have to be yearlings? And will you have any sub-yearlings or just yearlings?
I'm gonna lean on Chanda for that one.
Yeah, the JSAT, and no, that's why we don't have sub-yearlings. Yeah.
And I know you said there's only 3 sites per year, if I heard that right. So is it gonna be like Washington and Oregon? Are you taking recommendations or?
We don't see borders in the program, Laura. It's all just a beautiful estuary.
Wonderful.
I don't know. I'm trying to think. I think it's maybe 2 in Oregon, 1 in Washington. I can't remember exactly, Chanda, but it's.
Yeah, it's focusing on that Miller Pillar complex kind of around there, and then a little bit south. So definitely one would be in Oregon. And I'm just not sure where I always forget where the channel.
Yeah.
Splits. So depending on where in the Miller Pillar complex, it could be 1 in Washington, 1 in Oregon there in terms of sites.
Great. Keith?
I was just curious who's working on the website, because we have also have our restoration inventory that's going through a lot of updates right now, so there might be some good collaboration there, sharing information.
Yeah, we've got PNNL under contract to develop it. It's going to be a standalone website though, maintained by BPA, right? So going forward, it'll be BPA, BPA's dollar, BPA's sort of lift. Alex McManus, formerly with Wolf Water Resources, is transitioning to BPA, so he'll presumably still be involved. But we've got folks like Haida and Kayleen Gunn. I'm sorry, yeah, Kayleen and Sean, et cetera, working on that.
Thanks.
And also, they're really working hard to make sure it's not redundant to some of the other great things that are already posted, like through LSEP, Crest, I mean, and all of our partners. And so it's going to link to where to find.
Yeah, that's why I wanted to, to know so we could not be redundant, and either share some of that information or just talk to them about what they're doing.
Yeah. Okay.
Yeah, I think we're real quick. We're getting there, Keith, to that phase of the work where they've got a communications plan, they got sort of the skeleton, and then there's definitely going to be a lot of outreach in the next few months about how to link it and what to link it to best.
Great, thanks.
Awesome. Okay, any other questions? Okay, if nothing else online or in the room, we're going to start moving on to focusing on the ecosystem monitoring and a little bit of the action effectiveness monitoring programs and the results and how we can start to address the questions that Mark talked about. So I've got the first 6 questions on that, his last slide that had like the priority ones. So question 1 was got the highest ranked or the highest priorities, 2, 3, 4, 5, 6 sort of thing. So those are on your agenda, so you can at least look at those questions. And so then we're going to just discuss how we think we can address a lot of these questions just with existing historical data and what we're doing now, and then how to tentatively kind of like I think we're going to end on like recommendations of how we can tweak things or have more hypothesis driven sort of research kind of thing going on. Does that make sense? If so, I think I'm going to try to open this. Are you share my screen? So far. So do you want to come over here or how do you want to do this?
You want to try? Sure. I have a mouse.
Yeah, I could just do that. But first I gotta figure out how to share the screen doing this.
There's a share function in there that I was gonna say team or PowerPoint actually has a share function where it'll share 2 teams, but this is
there we
working well.
I'm gonna do this. How's that? Does that work? Can you guys on Teams, can you see this?
Yep.
Do.
Catherine, you might make it bigger. It's pretty small. Maybe do the full screen, like share the presentation, like hit the presentation button.
So it's not showing up for you as a full screen?
No.
Huh.
I think it's the screen thing that switches out.
Okay. Try again. Share this one? Yeah, no?
Yeah.
Okay.
Yeah.
All right.
There you
Can
go.
see
That's
now?
it. Yep, that's
All
better.
right. Do you want to just use this?
Oh, yeah.
Okay.
Okay, hi everyone. Thank you so much for being with us in person and on the call today. Mark, thank you so much for giving such a comprehensive overview of the CEERP program and the summary of the workshop. Today, Ian, Derek, and I will be talking a little bit about how we can use the habitat data that we collect over at the EMP program to answer some of these research questions that came out of the SM3 workshop. So yeah, I'll give you a brief overview of the monitoring programs, how it's set up for now. And then Ian will take over and talk a little bit about some of the work that we've done. And Derek will end with also talking about, besides this question, what other research questions we can address by, with the data that we have. All right, so at LSEP, we basically take care of two of the CEERP monitoring programs, that's the ecosystem monitoring program and the action effectiveness monitoring program. The ecosystem monitoring program, as Catherine mentioned, started like in the early 2000s, and while it was it's a stats and trends monitoring program, basically designed to compile ecological conditions of a range of tidal and freshwater habitats. Under this program, we study undisturbed or minimally disturbed wetlands from the mouth of the estuary all the way up to Bonneville Dam. And we basically provide knowledge about the ecological conditions that are changing over time, as well as provide a suite of reference wetlands, which then feed into the information into the action effectiveness monitoring program. Now, the AMR program is specifically designed to study the trajectory of restoration sites, pre and post monitoring, pre and post construction. And both of these programs, the data that comes out of it then allows project sponsors and restoration managers to adapt their future restoration projects and basically provide a lot of information to study the different evolutions and the climate change impacts on these projects. Keep doing that. So the ecosystem monitoring program has always been a huge collaborative effort. We over at LSEP study the habitat structure, which involves hydrology, soil, sedimentation, as well as vegetation. We also study the biomass part that goes into the food web. Dr. Joe Niedava from OHSU studies the main stem and abiotic site conditions. We also have Dr. Tanya Peterson, who manages the larger food web part of the program. The macro community is studied by researchers from University of Washington. That's Dr. Jason Toft and Terry Akula. And then, of course, we have Dr. Curtis Rogner, we have Jeff Grote, and everyone else over at NOAA studying the salmons. We, for a long time, also had April and Narayan, who came out with us to monitor the habitat structure, but as of last year, they're now helping NOAA with a lot of the fishing, and I think, Narayan, you said that you enjoyed it quite a bit.
Yeah, no, it's great. Yeah, fishing and then macro and bird.
Oh, yeah, macro stuff too, right. The AMR stuff also is managed by LSEP, CREST, NOAA, and UW. We, as part of this, we study the habitat structure, and this is specifically the level 2 sites. Of course, we have 3 levels of monitoring at in the action effectiveness. Level 1 is more specific research interested studies, which is mainly taken care of by the Army Corps. Level 2 is a big collaborative effort, as well as level 3, which involves hydrology, sediment nutrition, as well as some photo monitoring. And all of us in the room do that. So what are the specific EMP habitat objectives? The overall research question of the EMP is how are the sites or the reference sites changing over time? And as part of the habitat structure, we study how the inundation patterns are changing in these wetlands. We are comparing the vegetation, how that changes over time, how much sediment is accreting or eroding at these reference sites. And we also collect plant matter or plant biomass to study the difference in detrital and energy export when it comes to like the yeah, the plant matter moving around. So this is a map or like a visual representation of the areas that we study. Each of these sites are representative of a specific geomorphic reach. We have 5 sites that we go to every year. That's Ilwaco, Welch and Whites, Campbell's Slough over at Richfield National Refuge, and then France Lake as well. In addition to these, we also include Cunningham Lake for habitat conditions only, as well as Steamboat Slough to provide extra information about the detrital export that I earlier mentioned. So we started doing this a couple of years ago. We've always liked looking at how much data we've collected over the summer. And as you can see, we've done a lot of walking this summer. And in addition to that, Ian and Ona and Derek have laid a lot of ground control points and have flown multiple hours of the giant drone that we have. We've also been able to collect a lot of plant matter, a lot of soil information, a lot of vegetation information as well. We've also done this really cool thing about creating this large database that now feeds into our Tableau EMP hybrid report. And we also have a visual representation of how much data is available all the way from when the program started in 2008. And you can see that over time, the program has changed to incorporate new information, as well as in when we updated some protocols, we've been changing the way we've done the monitoring. And because of this huge suite of data that we've collected, we've also been able to address some of the SM3 workshop questions. Mark spoke a lot about this earlier, so I'm not going to go into it, but all I want to say is that this presentation is going to focus on the first question, how the climate and flow-related temperature trends restrict habitat availability, and how will this impact the utility of our restoration sites. And with that, I'm going to hand it off to Ian.
Okay. So to answer that question, we really need to know when and where habitat conditions are already accessible to salmon throughout years. And you also need to check what the major drivers of these conditions are. So salmon habitat availability. We like this slide a lot, obviously. So salmon habitat opportunity, basically for salmon to have access to a site, it needs about a half meter of water. If there is not that much water, it cannot access the site. Additionally, it also requires temperature in like okay ranges for the fish to be happy and survive.
And the 0.5 meters and the temperature are from bottom. And
bottom
and
and
Cornell or something like that, so.
So go there if you want to know why they picked those numbers. Well, so to get that habitat availability, we basically take the site hydrology and temperature data, combine it with the digital elevation model from our LiDAR sensor, and that gives us the salmon opportunity model. So this slide is a lot, so we're going to go to a different slide. This is France Lake on June 1st, 2023, at a water surface elevation of, I think it was 6.25 meters. It is covered for us. But that dark blue is where fish can access and are happy. That light blue is where it is wet but not actively accessible to the salmon. So it's still providing habitat for other things, and possibly some of those fish are going there, but it's not considered habitat. So on this day, 73% of the site was accessible to fish. And I'm going to jump to another day. So this is December 5th, 2013. This is a pretty average water surface elevation we see at France Lake. Just the first date I found, it had no importance. The date itself is not important. But you can see that channel is pretty well inundated, and it goes up into the wetland complex. 32% of the site is generally accessible to fish at France Lake. During the freshet, quote unquote, of 2021, the water surface was about 6.5 meters, and most of the site was accessible. The stuff at the north of France Lake is kind of a cliff, so that is never really accessible, but the site itself is activated completely at this time. This is Welch Island. And my gift is not working, that's so sad. Okay. But at a high tide, this is what the site looks like. If the gift is working, you can also see it at low tide, but that's okay. Maybe it'll work. Oh, good job. Nice. Okay, so out of low tide, that's what the site looks like. So you can see that about 40% of the site is activated during a tidal cycle. And you can go to this site and explore it yourself if you want to. So additionally, we also added temperature to this. This graph is super bright, I apologize, but every year, that graph on the top is showing the 7-day moving average maximum or something. So it's the metric that says, are fish happy at this site or not? And we've compiled that into that habitat opportunity bar graph below to show the total number of hours in each month throughout the time series where fish are happy. So in July, for example, that found that 50% of the time and all of the time series and data that we have, fish are not happy and inhospitable to their survival. Welch, for example, if I can go to the next slide.
So in the summer, like July, August, September is when the temperature is prohibitive. And we're, yeah. Okay.
Yeah. Is it still when it's, is it when it's accessible?
It's still accessible at this
Yeah,
time.
okay.
So, I mean, they're not going there, so. Yeah. This is Welch, that same time period, you can see it's significantly better, but still not great in that August month. And, yeah, but fish are probably still happier at Welch than they were at Bruns. Additionally, we added this new thing. Basically, this is a flood level. It will be expanded pretty soon with a lot of the action effectiveness sites as we start getting the lifeguard data processed. So this is Cunningham Lake, flooded at a water surface elevation of 3 meters. This is a pretty standard winter flood level. This is the 2-meter flood or 2-year flood level of about 5 meters. And you can see just how much more of that site is activated. Coming soon will be all of the action effectiveness sites will be added into this format, so you can kind of flood them as you will to whatever flood level you want. And then you can go explore this completely yourself if you want to. So it's on our Tableau page. So you go to Tableau and you wait for it to load. Could take a while. And you can click around on those hybrid graphs where it shows maximum minimum water surface elevations. You can change different sites by clicking the little cards at the top. To change the temperature. Once it loads, which could take a bit. To change the temperature, you go to the tabs at the top and click on that. You can mouse over anything and it will tell you some additional information. That's probably going to be expanded pretty soon. Additionally, you can flood sites to specific levels on that page. And I will let people know when I add more sites to it. Change the flood elevation by just typing the box once it runs. I'm going to turn it over to Derek to continue.
So, okay. All right, well, thank you so much. Thank you. Yeah, so just to reiterate, since we've been using Tableau extensively for our data management and analysis, over the last few years, we've really been able to make some new connections and tackle some questions that are emerging in the estuary. And we're doing so by producing these manuscripts that I'm going to touch upon right now. So one of these is looking at the ecological drivers of reed canary grass. And the EMP data up to this point has continued to confirm that hydrology is a critical driver of reed canary grass. With this graph here, there's a lot going on, so I'm going to quickly break it down. On our left y-axis here, we have a percent of time flooded. On the right, we have a relative cover of reed canary grass. And on the bottom here, we have like an elevational gradient here. And what we're really honing in on is when you see that 30% mark there, of 10% of the time flooded, we really start to see that increase in reed canary grass relative cover. And in addition to that, hydrology as that driver, in turn, we see these effects on soil chemistry as well, particularly salinity and oxygen reduction potential. And all those combined, we're looking to just get into a little deeper and see how those drive abundance of reed canary grass. In addition, we're looking into sediment accretion and how that has an impact in addition to sea level rise, how those interact. So what you'll see here is on this graph at the top, the low marsh and high marsh both do overall have net accretion, with the low marsh having a much greater rate of accretion here. And we see that due to elevation, sediment loading, as well as just inundation frequency, causing the low marsh to have that greater rate of accretion. And that is also stored down in this box in this block here. You can see the low marsh. Now, this is generally the case across our sites. We do see that the exception is Campbell's Slough, in which we see a net erosion. And that is due to, at the site, we have some grazing that occurs. So we have some compaction of the soil and also just a reduction in the vegetation cover. So with that sediment accretion and erosion data, we can see some implications of sea level rise across our sites. So like I said, you can see overall we have that net accretion. Here's Campbell's Slough here with that erosion. And these, what you see overlaid here with these dots over our bar graph, are some sea level rise scenarios created by the Army Corps of Engineers Lower Columbia River Adaptive Hydraulics Model. And what's included in that are 3 different scenarios at 0.5, 1, and 1.5 meters each over a 50, 75, and 100-year increment respectively. And what you can see here is that with this model, which is a more, worth noting, is a more aggressive model of sea level rise. But with this model, Franz Lake is the only one that is currently keeping track with those sea level rise changes. We do see Cunningham and White's keeping up with the more conservative parts of the model. However, overall, these sites are not accommodating or keeping track with sea level rise this far. It's worth noting that we are also using our LiDAR data to help reinforce and expand upon this analysis. And we're going to be working on that moving forward. Looking forward to getting these manuscripts to you all soon. So that's all I've got. So let's know if you have any questions.
Anybody have any questions? I'm gonna stop sharing. That's okay.
Yeah, one of the questions I had, was for you for the habitat suitability or habitat availability. I know it's greater than 0.5 meters, but do you all take into account like if it gets too deep, or is it sort of just if it's greater than?
At the moment, just if it's greater than.
Okay.
I think we should do otherwise, because then we have.
Yeah, no, I was just curious, because I know like in some areas, right, like it can get where they're not no longer optimal, and then they kind of spread out on fringe, right? So, I didn't know if that was a consideration, and maybe it could be.
Yeah. Folks on Teams? Any questions? And again, the presentations so far are just like the habitat structural information that we are collecting from the different programs, and like how those information can like feed some of these or address some of these questions. So really just right at this point, we're just talking about habitat availability and how it might change, just the accessibility of these sites and how they might change with climate change. So that's really a lot of the first and second questions. And we can tweak any of this modeling or anything in how we're predicting this, that kind of thing, if folks are interested in working on this a little bit more with us. Anything?
I got one question.
Yeah,
Well, maybe I'm stepping back a little bit, but you guys ever look at, instead of 7-day moving average temperatures, peak temperatures and actual temperatures? So I always like wonder what a 7-day average temperature really means to a fish. Because peak temperature is getting worse, or is it?
So the percentages were all just based on the actual hourly temperatures.
Right, but do you look at like amount of time this fish is exposed to like the highest temperature of the day, or is that changing, or are they getting,
I think
exposed to
Jim might-
temperatures as well?
Joe might do that for the EMP sites. So he might talk about that next, but that's just the EMP site, so not the action effectiveness.
No, I know a lot of people use 7-day moving average, but I never understood why, so I'm curious.
Yeah, yeah.
And that's even better, the loggers are, like on the sites, right? So like they're at the elevation. So
Yeah.
it's not, yeah.
I can say a little bit about the 7-day. I believe it was an EPA kind of metric, and the idea is to show that it's not just a spike in the heat or anything that might be bad, but it's a long-term effect of high temperatures on fish. So it's a way of integrating kind of an overall temperature effect. That's the way I understand it anyway.
Great, thanks, Curtis. Anything else?
Yeah, it's a programmatic one. Just wondering if folks are leveraging Tableau or have any questions about it and don't need to talk about it during the year. EPA is always trying to figure out what's the best way to get more data out into the region, more within CEERP and across the larger just region. So that folks can feel like they're connected into what the CEERP program is providing, what the Estuary partnership is providing. Yeah, it's not enough, it's easy to crack, but I think Tableau's where we are, where the Estuary partnership is now, and where a lot of the data is flowing to. My understanding is entities are able to establish their own, what do you call it?
Profile.
Thank you. To manage their own data as well. Just didn't know if it was something that's being used by other entities. And I guess a more specific point, somewhat related, is thanks for the slides that demonstrate the impacts on restoration sites, reference sites. How do we create a conversation with partners, or do we need additional conversations with partners on how to incorporate the EMP, AMR data into future site planning? So these are just kind of the programmatic questions we're always wrestling with. What does this mean for future planning? How do we do this in a way that feels like we've got? I wasn't at SM3, but there was a lot of understanding that there's a lot of data out there. The meeting itself was really useful for people just to get in the room and understand what that data was and who was doing what. We continue to prioritize getting as much as public, not EPA, but encouraging sponsors and everybody who's doing work under CEERP to get stuff published as much as possible, because we're really adamant that we think primary publication is a good way to prove out the state of where we are with CEERP. So just from EPA's perspective, we are trying to make sure we're well coordinated with Estuary Partnership, CREST, COT, DFW, to make sure this data that is flowing and continues to be collected is also useful. So I know there's Verdict members on the phone as well. And as a follow to all of that, stream of consciousness, I apologize. We will continue this kind of conversation at the annual Verdict meeting.
Yeah.
December 13th. So if you're not on the list already of that meeting and you're interested in The current state of affairs, both the restoration and monitoring, there's more discussion that will be happening on Friday the 13th.
Yeah, it's true. Conservation Day, yeah, for real. I think that the Tableau and how to make this data, the data and the results, I think that's relevant for all of the presentations, you know, like all of these different things. How do we tell these stories that, you know, resonates and is useful to folks? So keep that in the back of your minds, is like, how do we do this better? Because I mean, like, our annual reports aren't being read. So, and they're not the, you know, useful thing. So like, is Tableau the mechanism? Is there some other way of trying to make these data and these results useful for you all in your restoration designs and how you evaluate projects, that kind of thing. So let's keep that in the back of our minds. Amy, do you have a question? Your hand's up.
I do. Can you hear me okay?
Uh-huh, yes.
Okay. Yeah, I just had one specific question just because it was very fine print on the screen and couldn't see it very well. But I think you said for the habitat accessibility, you're incorporating both depth and temperature. So you showed the graphs that kind of showed each individual, but I wasn't sure if the plot at the bottom indicated the two combined metrics for inundation and temperature and when those reduced accessibility. Was that the idea?
It was only temperature included in that bar graph. We felt it was better to separate them completely because it doesn't really show, it's hard to communicate that over an entire map in a two-dimensional space what three-dimensional temperatures are doing. So it was just too much. So I simplified it.
You separated it?
I
Yeah.
separated it.
Does that answer your question, Amy?
Yeah, that does answer it, but I do think it would be informative if you could figure out a way to combine the two metrics together.
Yeah, we're trying, yeah.
Sounds like a good idea. All right.
Sorry, I had one more part of my question.
Uh-huh.
I just wondered if you're looking towards some of the future climate projection information and trying to incorporate that into what accessibility might look like under different climate scenarios with both temperature and changes in inundation.
I think Joe's going to get into this a little bit in the next presentation, just a little bit for the EMP. And I could be wrong, and Joe might want to yell at me for that. But we could wait till Joe is done and then return back to that question. Is that okay, Amy?
Mm-hmm.
I think that's a good one. Okay. Thanks. Jen? Jen?
Yeah, hi. My question, maybe I should also wait till Joe's presentation, but I'm going to put it out there anyway. I'm just curious if, to what extent salinity is expected to change with sea level rise, and is that something that you're taking into account with like vegetation stability of like plant communities over, you know, longer periods of time?
I'm going to go ahead.
We aren't really specifically looking at that, but salinity is one of the things that we measure, that Joe measures, so we should probably, you know,
and I'm
let him talk.
Yeah, and I'm gonna punt to somebody else in the room as well.
So that's something that we've done a bit of work on in the past. It seemed often I'm planning on doing work on in the near future. So we'll be able to look at modeled salinity changes under sea level rise.
Yeah, that's great. I've been a spectator / like involved in monitoring some coastal restoration sites on the East Coast that were planted with bald cypress that are likely to or have already been experiencing brackish water intrusion, and their, you know, future longevity is in doubt. And I know these are not forested wetlands, but just like thinking about plant communities being able to persist in the future with sea level rise is a big concern.
Great.
In the work we've done in the past, I think Reach B is the only one that has that impact.
Oh,
But
okay.
it's a probably a fair-sized impact, so there'll be significantly more salinity intrusion into Capilano Bay primarily.
Oh, interesting. Okay.
That's because Reach A is already salty enough and Reach C
Yeah.
is just not gonna get there.
Yeah.
Okay. Great. All right, so watch out for Reach B. Okay. We haven't really talked about this, but one of our colleagues is into emerald ash borer and how that's gonna have an impact on the riparian area, especially like around Sabi Island, that kind of thing. So, but that's not relevant necessarily to this conversation. So should we move on to the next presentation? We're kind of getting into it a little bit. Sound okay? Joe, are you gonna show your screen?
Yeah, I
Okay.
can. Let me know if you can see it.
We can see it.
Is it big now?
Yep.
Yeah, okay. All right, thank you. So I'm gonna talk today about the relationships that we're seeing in our water quality monitoring data with respect to habitat quality, in the sense of the relationship between the location of some of our EMP sites relative to the main stem, and then over time how interannual variability in the timing and magnitude of the fresh hit impacts these sites. And you've heard me talk, many of you have heard me talk about this in different ways as we've been trying to disseminate our data, but I'm going to do it slightly differently today with a kind of the idea of setting up some of the talks after me, where we are agreeing to kind of focus our manuscript writing on this idea of developing, you know, a way to evaluate the different aspects of the EMP program, the food web and the fish, by characterizing these sites with respect to a couple of these things. So I'll try to make that more clear here. I think everybody now has the gist of where these sites are. This is just the data from the EMP program. We have these 5 sites that span the geographical range as well as the different reaches. And I think what we can learn from the differences in these sites is very helpful. I'm going to blaze through these two because I don't want to waste everybody's time if you already know this, but the 2 sites that we have in the reaches closest to the ocean are Ilwaco. That site is brackish, to answer a previous question, and you know, so we see salinities there higher than 15 in parts of the year. Welch on the right of your screen is in the middle of the river on an island. They kind of look like this. On the left, that's Ilwaco in the early or late winter before the marsh starts growing. Welch is shown there. So I'm just gonna what you're also seeing on these figures is these are maps from the Estuary Partnership website. Is the green is mapped to be habitat, salmon habitat now. The yellow is potential habitat that's behind dikes and levees that could, through restoration, possibly be recovered, and the red is lost habitat. But so there's another site. This is White's, also on an island in the middle of the river. And then further upstream is Campbell, which is much less connected to the main stem. It has the water, the channel is approximately 1.5 miles from the main stem. So rather than being directly connected to the river, it's a meandering channel like many are. And so it's representative of that. This is was mentioned, the grazing on the right. We do see cows in there, but otherwise, you know, this is Ridgefield Wildlife Refuge, and so it's a habitat for many animals. And finally, the gorge, which is looks like it's well connected to the main stem based on how close it is to the channel, but because of the beaver dam that's there, it is another example of a less connected site. And so I'm going to use these connection to sort of put our data in context. There's the beaver dam. Most of I'm talking about water quality monitoring using sensors like this. So the YSI XO2, which can measure not just temperature and water depth, but pH and dissolved oxygen, turbidity, chlorophyll, and a number of other parameters. I'm not going to talk about any of those today because we don't have time, but I'm really going to focus on temperature and the difference between main stem temperatures and off-channel temperatures throughout the EMP program. So somebody asked about the 7-day moving average and about other types of ways to look at this temperature data. What I'm showing here is the Columbia River main stem temperature from 1995 to 2023. The number of days per year that the temperature is above 19 degrees Celsius for the month of May through July. So 3 months that kind of capture when fish are there, when it's starting to get warm, and when the freshet has a big impact. And what you see is over this period of time is a few years that are much colder than average and years that are warmer. So the blue dots are the number of days above 19 degrees Celsius. The histogram at the bottom, the bars are a z-score, which is a way to evaluate how much different from the mean individual years are. So if the bars are below -1, then it's a lot colder than average. And if the bars are greater than 1, then it's a lot warmer than average. You also see a trend here. This warming trend over this 30-year period suggests that the number of days per year that the main stem is warmer than 19 degrees Celsius has increased by approximately 10 days. So this is a warming trend. This is supported by the paper that came out in 2013. Many of you probably contributed to that paper, but it was a modeling study of Columbia River temperatures since before the 1900s, and so captures pre-dam temperatures. And they basically showed us the statistical significant warming trend that matches what I'm showing you here. Some of the differences is the model doesn't capture these really extreme events like the 2015. You can see the very warm year in 2015 and the 2010, 11, 12 or the very cold years. So in context of changing climate, you know, the river's warming, at least there's periods of time when it's too warm, and that's increasing. And what I want to just highlight then is that the EMP program has been around long enough to capture some of these big variability years, right? So we have data from these cold years centered around 2011. There's 3 of them that are all have very low z-scores. We also captured the 2015 period as well as the 2021. And so those are very warm years. Then we have some average years, and then we have some cold years. And I think it allows us to put in context the prey data, the fish data, in a way where we can compare. Well, this is what it's like in cold years, as well as like in warm years, and what do we expect in the future? So that's where I wanted to go with this talk today. If we look now at our EMP sites, this is a graph from our Tableau page. This is just taking all the data for all the years, and the takeaway from what you're looking at is that Campbell and Franz have more time in the summer, primarily where we're above 19 degrees. So those we know in general, lumping everything together, Campbell and Franz are warmer sites. Ilwaco is colder, and Welch and Whites are in the middle. So just start with that and then kind of look into this a little more. Taking into account what makes the river warmer or colder, I think most people agree. One of the things is the size and duration of the freshet. So here's the black lines you're seeing are a maximum and a minimum from the data set for a given day of the year. So they don't represent any given year, but the blue line does. So you can see that in 2011, the size of the freshet, the maximum numbers actually came from the year 2011. Whereas in 2015 and 2021, the freshet was very low. And then there's lots of years like 2013 that are in between. So the relationship between this and how it impacts these individual sites is one of the questions. That's not me, right? Okay. So the variability between those two extremes looks like this at Campbell Slough. Like you can stand there, it's all probably close to 1/2 meter of water in the middle, but barely. And then on the right is 2 years later when everything, including anybody standing there, would be another 6 feet underwater. And so really big differences. Most of you know that, but this obviously impacts habitat suitability. Okay, I have a few graphs that look like this. It's just plotting the wetland condition for temperature, same indicator, which is the number of days above 19 degrees Celsius for each year. And the blue is the main stem, which is the data I already showed you. But it looks a little more scattered because it's a shorter period of time, right? 2011 to now. So for Ilwaco, water temperatures from this perspective are always lower than the main stem. Ilwaco is colder. And what's the reason for that? Well, it's because the ocean water impacts Ilwaco significantly, and the ocean is colder than the river when the river's warm, basically. So some years they're closer, and some years they're not. But the trend is Ilwaco is a colder site than the main stem. Whites and Welch are about exactly the same as the main stem with a tiny amount of variability, and they're all about the same as each other. And so we can characterize these as being sites that are highly reflective of what's happening in the Columbia River itself. And that's been demonstrated at both sites over a number of years. And then our sites in Campbell and France are the opposite of Ilwaco. They're much warmer than the main stem when the water's warm, when it's above 19 degrees. And so we see many more days per year at Campbell and France. And so thinking about connectivity, then obviously it's not rocket science, but the data shows it that the less connected, the warmer the water is, and to the extent that it makes it good habitat or not is something to think about, especially with respect to looking at the restoration sites or future restoration sites. So that same data I'm showing here instead, this is just the difference between those two, the difference each year between the two sites. So on the left are between the site and the main stem, sorry. So Ilwaco, as I showed, is always a lot colder. The axes are all the same for all 4 of these graphs, so you can compare them from one to the other. So Ilwaco tends to be a lot less days of above 19 degrees Celsius compared to the main stem. Whites and Welch are about exactly the same, and Campbell is much higher. And then I just draw your attention to the interannual variability, and we can ask what's causing those things. Is it a big, large freshet, or is it hot summer air temperatures? And those are what we're looking to move forward with. But I will say that I think in this framework then of what you're looking at, we can also interpret the prey data. We can interpret the hopefully the fish data. And just to look at one in particular, it's complicated when you start looking at the variability. But here's Franz Lake, always warmer, but sometimes not. Like 2022, it was not warmer than the main stem. And I'm just showing 2022, the main stem temperature and the Franz Lake temperature. And you can see that for the period of time that we were talking about, which is the beginning of May to the end of July, Franz and the main stem had the same temperature. And that's because there was a large late freshet in 2022, and Franz was completely underwater for that whole period of time. So that's probably good salmon habitat. And that's the reason why. So every single year has its own nuances. And what I've been trying to do here is show how maybe we can categorize them to interpret the data better. And here's just an example of Franz, right? Like in most years on the left, there's lots of water behind the beaver dam. The year that the beaver dam got knocked out is shown in the middle, and obviously not great habitat because it's basically just a creek. And then on the right is an example of a big freshet where all those trees are underwater. So the really big variability is an asset when the EMP program now has enough years to be able to compare, I guess is my message today. So wetland abiotic conditions such as water temperature, and I never talked about dissolved oxygen, but it's super interesting. I just didn't want to spend too much time today. Both of those can be used to characterize salmon habitat. And EMP sites are temporally sampled across high and low discharge over the period of time, and extreme temperatures. And so using those contrasts to interpret the data is the goal of our group moving forward this year with the manuscripts we're writing. So I think I'll leave it there. Catherine, I don't know if that was the right amount of time, but hopefully time for questions.
Great, Joe. I'm going to start you off with a question that Amy asked about looking at climate projections. And I think you kind of had talked about like using 2015 as like if climate projections mimic what happened in 2015, could we use those as a way of like looking at accessibility for these habitats? And maybe, Amy, I'm not doing that justice, but I think that was what you were trying to ask, is whether we had looked at like climate projections and whether we could like speak to with our data, like what we might see with availability and accessibility, and temperature might be an issue with if we use 2015 as a representation of climate conditions or climate change conditions.
Well, when 2015 happened, it was associated with the North Pacific marine heat wave, and it was a once in a 1,000-year event, and there was no snowpack. And many of you remember all the things that happened, and algae blooms in the ocean, and fish migrating into the river. There was population that the entire run died, a few things like that. And so that's what we have been talking about is, well, if 2015 is going to be something that's more common in a warming climate, then we should be looking at that. It happened again in 2021, and I think again in 20, we don't have the final data in, but it's happening. It's not a once in a 1,000-year event anymore, and so I think we should be thinking about it like that. And it really, obviously, most people understand this, that it really depends on how much snow is still in the mountains in the end of March, right? And then that depends if there's a big snowpack, but it melts too soon, or those types of things. We don't really understand those, but yeah, that was my intention before and still is that in addition to the gradual warming I showed, and has been shown in published papers, we could see more years like 2021 and 2015.
Great, thanks. Any questions for Joe?
Yeah, kind of trying to apply that to, you know, you had said something about like taking that into consideration when you're thinking about your restoration actions. You know, obviously most of the warmer sites it's warmer upstream, right? Is that the general trend?
No, well, go ahead, Joe, sorry.
The river itself, for all useful purposes, is exactly the same temperature between the locations of all these sites, except for Ilwaco.
Okay, so it's more around like, just think about it in terms of like how many connections you have or how much water from, okay.
Yeah.
So one thing we were discussing offline before this was in the gorge where you have high elevation streams, alluvial fans, you might have sites that are a little bit cooler, longer, but we don't really sample those in the EMP, so we don't really have that in the hyporheic exchange, all that kind of stuff. So we don't really have that represented in this, but I think what Joe is saying, and what we found with our cold water refuge work with under EPA is that the main stem is, you know, the EMP data says the main stem is like hydrologically uniform, basically, or tempered. It's homogeneous, you know, surface and bottom as well as latitude or longitudinally. So anyways, the only way fish can really get cold water is to get off the main stem, basically, for the most part, except for like, you know, down in the mouth or the true estuary.
But I think Franz, you know, Lake is representative of a gorge site where there's water from the mountains coming into it. We don't see any colder temperatures there. But that's a very complicated site with the Beaver Dam.
Mm-hmm. Yeah. Amy?
Yeah, I just had a question related to that, actually. I was wondering where the location of your temperature sensor was relative to the Beaver Dam, if it's below it or above it.
It's behind it by about 200 meters, or like ways back there. Yeah.
Okay.
Yeah.
And I just wondered if you did see any cooler temperatures in the years that the dam was in place or not, if you could relate that at all.
The dam was in place the entire time except for the winter and spring of 2021. And so we didn't we do have the data for that, and then it got complicated because that was the 2021 heat wave in the end of June, you know, the other once in a 1,000-year event. And I guess the beavers figured they needed their dam back because they built it back right after that event. And so it was warm, and then the beaver dam was built, and it went back to how it used to be. So it was a strange time. Like, I guess in the winter time the dam got taken out somehow, and then it got built back like in July, immediately after that heat wave. It was a full-size beaver dam again within less than a month. So it's really hard to interpret that, but we do have the data, and it shows the temperature stabilizing in August when the water levels were high again. Yeah, so I don't know if that answered your question.
Yeah, I think so. I mean, that's the question, I guess, is if the dam can provide any kind of mediation in temperature because it's deeper and potentially holding some of that hyporheic flow.
Yeah,
a little bit longer.
I think so. It definitely, you know, kept more of the slough was inundated, as I showed in the pictures there, a lot more of it. Yeah.
Okay, moving on to the next presentation. Okay. Tanya? I think she was having a hard time logging in. Tanya, are you there? Oops. Hey, Tanya. Let me see if I can text her.
I think Tanya's having technical difficulties connecting. Maybe she could go later.
Later? Okay.
Yeah, do you want us to go ahead or wait for Tanya?
She says go ahead.
Okay,
Okay.
Harry's totally ready.
Awesome. Thanks.
Here we go, forging ahead. And my name's Jason Toft again. I'm just giving the big picture overview for our group, and then Carrie's going to take over. So by and large, the last decade or so, our lab's been working on looking at the juvenile Chinook salmon diets that are collected, and also the invertebrate prey resources in benthic cores and in Houston toes. So yeah, we're in the push here to get stuff out the door and published. Carrie just submitted yesterday, I think, in a manuscript to Transactions of the American Fisheries Society on our juvenile Chinook salmon diet data. Yeah, and so we're looking for next steps here and how we can really roll this data all together and make something more of it. So with that, I'll let Carrie take it away.
Thanks, Jason. Can everyone hear me and see me okay? And see the screen? Okay, great. I'm just going to give a real quick overview of why Chinook salmon, just so I think we're all on the same page for Chinook. But broadly, juvenile Chinook are the most estuary dependent of the Pacific salmon species. So they spend the longest time in an estuary, and first year growth is linked to survival to adulthood to spawn. So the more they grow, the higher the probability that they will return to spawn as adults. And there's a lot of other advantages to getting bigger. The bigger you are, the more you can handle toxicant loads, the more you can fight off infection and evade predation. So broadly, what we have found with Chinook diets is that they, since the beginning of the study, they do not appear to be prey limited. And among the top sites where they are found, which is Campbell, Welch, and White's, and they're mostly at these sites for sampling reasons. Jeff might speak more to this, but Franz has some challenging issues, sampling challenging issues, and Ilwaco, it seems like by the time they get there, they might just pass through. So most of the salmon are at the middle three sites. And what we see is they have pretty full stomachs and they're getting a decent amount of calories. So it's comparable among those sites. So the plot I'm showing you is a visualization tool, and what it does is it takes multivariate data in multidimensional space and it squishes it down into 2 dimensions. So what we are looking at is a plot of what young sub-yearling Chinook are eating, and it accounts for the number of the prey, the weight of the prey, their food, and how often it occurs in the diet. And then it squishes it down into this 2-dimensional space. And what you see labeled are the top 8 or 9 things that salmon eat. And then arrows signify the strength of the relationship. So the longer the arrow, the more important the prey is to salmon. So since 2008, there have been 3 key things that salmon eat. One is amphipods in blue, chalidocerans or Daphnia in yellow, and then dipterans in green. The dipterans are mostly chironomids. So the table inset shows the energy density of these prey, and it's really like how nutritious they are, the calories that they're getting from them. So you can see Cladocera, for example, are not very nutritious. The other top prey are a little more nutritious, and then there's some insects that are not as important in their diets that are very nutritious. These energy densities are taken from estuaries along the West Coast, So they're not specific to the lower Columbia, and we do hope to eventually update the energy densities to reflect lower Columbia species. So what we see is the most upriver site, fronds, is where the Chinook are mostly eating wetland insects like these dipterans. And then as they head downstream, they incorporate chaladosterans into their diet. This has been more common since 2016. Chaladosterans are not very nutritious, as you see, but they're prolific, they're large, they are easy to catch, they are warm water tolerant. So it's likely that they're like a supplementary item in their diet. And then as they head downstream, they incorporate amphipods more. They have amphipods as well as Campbell, but amphipods are saline tolerant and they're more important downstream. This next plot is looking at the same data, but broken down by size of fish. So it's the index of relative importance on the y-axis, which is, again, the number of the prey, the weight, and how often it occurs. And this is by year. And on the right are the top 3 sites, Campbell, Welch, and Whites. These are the fish that are like 90% of the fish in the EMP diets are from these sites. And then I broke up the size of sub-yearling fish into 3 bins. We can call them small, medium, and large. And the takeaway for this slide is just, if you notice the colors, all sizes of fish are eating the same top 3 prey. So amphipods in blue, chaladosterans in orange, yellow, and dipterans in green. And this percent of relative importance, it adds up to 100%. So as you can see, it's like jaggedy lines, meaning there's not like a third of the top prey, but it seems like they have a top prey, and when it's not available, they supplement it. For example, if you look at Campbell, the top row of plots in 2017, you see that chironomids or dipterans, the green, it plunges to nearly 0, and chaladosterans, which are not very nutritious, are the most important prey for Chinook that year. And likely their preferred prey was not available, and so they supplemented their diet with chaladosterans. More nutritious insects are also important, as you can see from the rest of the colors, especially later on in the year. So what we have found overall is that the Chinook salmon do not appear to be prey limited. Their stomachs are pretty full. The highest abundances are still every May, so there aren't any trends that are clearly changing. And our statistical analysis results, so it showed the Waco diets had the highest caloric intake, but they were very few of the sample. So the top sites, again, most of the fish that were Campbell, Welch, and Whites, they're comparable. Their stomachs are full and they're getting around the same amount of caloric intake. There were some instances where Campbell there was more nutritious insects in July for Campbell fish. July has the highest energy from these nutritious insects, but there are fewer fish that are left. The majority have left by July, end of July. And overall, the smaller fish do better in terms of stomach fullness and calorie intake compared to big fish. So with everything in life, there is cost, and metabolic costs for juvenile Chinook are a direct function, among other things, of size and water temperature. So growing fish have higher metabolic requirements, and higher water temps increase digestion and gastric evaluation. So as a fish grows, it needs more food to maintain its metabolic processes and keep growing. So as long as it's not prey limited, it keeps growing. Higher water temperatures makes it have higher digestion and higher metabolic needs. And so it has to keep eating more just to maintain these processes. And then in order to grow, it'd have to eat even more. So I'll try to be brief on this slide because Joe talked about temperature. But these are average water temperatures. This plot, year is on the x-axis, temperatures in degrees C is on the y-axis. And then again, the top 3 sites are on the top, and then on the side are the top 3 months. These are the months where most fish we had most of our fish sampled. The black horizontal dotted line is 15.5 degrees C. This is what the independent scientific group recommends for optimal rearing for Chinook. I saw Ian had 17.5. There's various numbers. But I guess what I'd like to point out is that you can see the trend towards warmer water temperatures. And then by the time you get to June, salmon are mostly in water temperatures that are not optimal for fitness. So we know they're eating from our diets, but are they growing? I guess that is an unknown if they are eating just to maintain metabolic processes while they're increasing water temperatures, or are they growing? And how will this change their fitness, like their survivability to return to spawn? How will this change migration patterns? Could there be a predator-prey mismatch where salmon are leaving earlier than their preferred prey are available? So we advocate for using our data to inform a bioenergetics model, which can help us get at growth, like realized growth, amidst all the things that they're dealing with in the Lower Columbia. And eventually we hope to update the energy density values. Right now, that the table I showed you are energy density values taken from the West Coast, but those are not specific to the Lower Columbia. So we would want energy values. We would use ash-free dry weights to calculate values that reflect specific species that they eat in the Lower Columbia and specific life stages so that we can best inform the model. And Jeff and Curtis will take it from here to talk more about the bioenergetics model. Thanks.
Sorry, Carrie, Rose, do you mind?
Yeah, I was just curious about your methods. Are you looking at the stomach contents of the fish?
Yes.
Okay. Do you do any sequencing or is it like visual inspection?
Nope, our lab is taxonomist, so it's counting and weighing and IDing.
Thank you.
Yeah, the stomachs come to us.
Any other questions? I'm going to go back to Tanya. Hey, Tanya, are you able to log in?
We'll see if I can share my screen. That's always the thing. Sorry, everyone. I have a new computer that has a camera that works, but it's having some connectivity issues. So I tried to join the meeting probably 8 times, and I successfully got through some of it, but then I couldn't hear anyone at the end. So I can try to share. Do you want to do this now and then the bioenergetics after? Makes sense?
I think it makes sense to go ahead and do it, Tanya. If that's okay with you.
Okay.
It works.
Let's try. See if this works. I just hit PowerPoint Live. I don't know if that's a good idea.
Hey, yeah, we can see it.
Okay, is it big or is it small?
It's perfect.
Okay, sweet. I have really a series of just snippets of things that we're working on and planning to do, and so less of a cleaned up data story with lots of graphs to show and more just of an idea of what we're working on. So hopefully that works for everyone. This kind of falls under the theme of habitat quality, and the things that we in our lab, Joe and myself and students and collaborators work on is looking at the various aspects of water that involve how good is the water for the fish just to be in. So water quality that's found in the habitats, but really from the viewpoint that it's influenced by plankton and microbes and fungi and everything. And then I think taking the water quality sun data, the oxygen to determine ecosystem metabolism, which kind of again is that link between the biophysical and the biological, and then kind of filling out the food web by looking at stable isotope tracers to inform some of what Carrie was just talking about. How do we figure out what the salmon we're eating, today, last week, a month ago, and that hopefully will help us think about the whole system spatially and temporally. So that's my hope that as we get further along in the analysis, that will come together. So we're all here because we're talking about restoration and the importance of it. I don't think that needs to be explained to anyone. What I will say is that the thing that I'm interested in as a sort of an aquatic microbial ecologist and a food web, interested in the food web, is thinking about how the physical complexity that that's in the river, either naturally or that we've created through restoration projects, how that transforms or how that leads to changes or improvements in biogeochemical function. A lot of that we still don't fully know, so we're investigating those relationships through our work, and then ultimately hoping to be able to predict what benefits to salmon populations those changes could have. So within that topic of physical complexity translating to biogeochemical function, as I said in the beginning, we have some work that focuses on net ecosystem metabolism. So is the river a source of primary production in situ, or is it more that there's material kind of being transported down and that's fueling respiration and metabolism? So those are things we can answer by looking at the hourly dissolved oxygen changes. We look at species composition and interactions, and that mostly at this point has been just looking at the species composition, but knowing that the plankton are both prey for the prey of the salmon, and also that they influence kind of the greater water quality in the habitats, and then extending on to food availability and how that supports fish and consumers. So the first thing that we've been working on and hopefully will finish writing up is a study of ecosystem metabolism in the Columbia River and Willamette rivers. This was student work over the years ago in our lab supervised by Joe, but we're working on really looking at the compare and contrast between the Columbia, where there's more gross primary production and really algal activity because the water's clearer, compared to the Willamette, where light tends to be more limited. So these two graphs that are here, they're a little busy, but what they're basically showing, that black line in the middle is the net ecosystem metabolism, the difference between production and respiration. And in the Columbia, you can see it's greater than 0 most of the time. So this is just kind of a year snapshot from starting in July on the left to August on the right. And in the Willamette, it's really closer to 0. So really a net balance. Respiration is about the same as production. So these are things that influence whether there's a lot of organic matter available to feed into the salmoniid food web and other animals too. So we're interested in kind of capturing that, because that really sets the stage for what's in the water. What's the maximum amount of organic matter in the water that can be incorporated into the food web? And then we can then compare that to what's coming in with the plants. And we look at the plant detrital, live and dead detrital matter as well. And then this is not intended to be viewable at all. This is a figure from a paper, but we can use the data from species composition to identify key thresholds in environmental factors that might be important for capturing kind of the state of the ecosystem. So what this is a machine learning algorithm that allows you to take species composition data and identify places where there are kind of bigger changes. And so we know, for example, with phytoplankton, there's a huge difference in nutritional quality between certain types. And as we've been talking about temperature a lot, as temperature increases, you tend to get species that are less nutritious, which means if they're less nutritious, then that means that the prey that are eating them are less nutritious, and so on. So from an ecosystem perspective, it's kind of a way to capture that integrated information. So I'm hoping to do that with our data. We've done it. A student of mine did this in the Lower Columbia, looking at habitat that was conducive to the formation of algal blooms. And so we identified a river discharge volume that's associated with a shift from sort of a more marine habitat to freshwater. And so I think you can do that for temperature, for water depth, or discharge or whatnot. So the plan is to use plankton species composition, phyto and zooplankton, to identify these ecologically important thresholds in environmental variables that will help inform what the habitat quality is for the salmon. And of course, salmon food webs we're interested in. So there's two kind of ways to think about this. Carrie just did a nice overview of the direct observation of stomach contents and looking at the diet. And we're going to use a different approach to that. So to back up, there's the diet that influences what the salmon are eating, what they have access to, and then there's water quality that influences kind of how what potential stressors there might be on the fish as they move through. And that includes pH, dissolved oxygen, low or high, and then the presence of any toxins or chemicals that might be around. So for the water quality, we collect lots of data, and this is the sonds that are in the off-channel sites in the habitats that Joe has talked about before. I'm just showing here some kind of snapshots, not for the purpose of looking at all the information that's in them, but each of these things, pH, dissolved oxygen, and chlorophyll, are all things that phytoplankton and the lower food web do and influence salmon directly. So if the pH gets too high, that's not conducive to salmon growth and survival. Similarly with dissolved oxygen and chlorophyll. These are all used as indicators of water quality that have state and national metrics. So we look at them as also indicators of whether the habitat is suitable. And so the plan here is to do sort of some companion work to look at these variables and how similar they are to the main stem river, much like Joe was describing earlier with the temperature. So you can think about sort of the evolution of a habitat like a shallow habitat at Campbell or Franz, and how as the water becomes more disconnected, those habitats can become quite different than the main stem. And I think we can think about that in terms of the departure from sort of a main stem state. And then for the fish diet, so the approach that we take is to supplement and complement the direct diet observations by using tissue stable isotope tracers to infer what the salmon might have been eating. And I think as a total data set, there's some potential things we could really dig into. So the stomach contents are what Carrie was just describing, and they tell you what the salmon ate in the last little while. And then if you take different tissues that are in the salmon, from the mucus on the outside to the liver tissue to muscle and fin, you can get an idea of what they've been eating over different time scales. And so I think there's some potential to capture sort of that integrated view of what they've been eating over the last month or so, which is kind of aligned with our sampling schedule. So the mucus is a shorter turnover time than the liver, which is a shorter turnover time than the muscle and the fin. So we can start to look at that. And we've got data for those different tissues, and I'm just cranking through it to try to make sure we have good enough coverage to come up with models that will tell us something useful. So just to give you a little bit of a behind or under the hood look, this plot right here, again, no details to be remembered exactly, except that it shows you the isotopic signatures in carbon and nitrogen for all the dots are salmon, and the larger dots with the crosses are the sources, the things that they're eating. So we collect information on copepods and amphipods and terrestrial insects and nematodes and oligochaetes and all of these guys, and put them into this model to see what the salmon could be eating. And so at the end of the model, if it converges properly, you get an idea of the dietary proportions based on comparing the signatures between the fish tissues and the prey. And knowing what the stomach contents are is really, really powerful, because it can allow you to more accurately specify what the starting point is for the model. And that's really, really awesome. And then, so we could ultimately separate some of the different types of fish tissues to see if there's any difference. And if there isn't a difference, it means they're probably eating the same thing during that period of time as they're swimming through or occupying the habitats. But if they are different, it might mean that they are doing different things depending on where they are or when. This is very much in progress. So using the different tissues that we have, we could predict different timescales. And another strength of the Bayesian models that we're using is that you can specify concentration dependence. So you can either basically sometimes there's a lot more of a less preferred prey item around, so the fish will eat that. You can kind of put that in there for consideration. But you can also, I think, using that feature, specify prey preference. So you could say, well, you could set that up there as an option. So things we can explore as we think about the use of bioenergetics modeling. You could think, putting in more valuable prey in terms of energetics and things like that. You can sort of test out to see if that works with this data as well. And then, hot off the press, I've been doing some modeling runs just to see what comes out. The more data we get, the better these are. And so we've been collecting data on fish for a number of years and on the prey items. And it's kind of tricky because you don't always get the same prey at all sites all the time. So that you have to sort of have enough data for this all to be robust, and we're getting there. So this is just this is model output data for Campbell, Slough, and White's Island, and it's kind of faint, but the different prey items that we tend to see the most. So amphipods, chironomids, copepods. WB is water boatmen. They're big and easy to get, so they end up getting in there. And then a variety of worms. And it just shows that for Campbell, there's sort of a more even distribution of more things, whereas at White's in this particular run, you see there's a greater proportion of copepods that might have been abundant at the time. So this is not the last final story, but these are the kinds of plots that represent the output, and I can have a closer look at what makes sense because we have stomach content data to compare to, and so that's we're hoping to get through and try to look at them in different groupings, so you can look at different years, sites, along river distance, and things like that. So that is a kind of a snapshot of what we have going on. The next steps would be to look at the dietary proportions as a function of the different variables I just mentioned, hoping to use things like stomach content and prey fields to inform priors, and that will help make the model more robust. And we can think about using the model to identify gaps that we may not be able to sample, and so it might illuminate things that we don't know. So that is all that I have to say now. Hopefully, starting point to really dig into some of these analyses a little more.
Good, thanks. Any questions for Tanya? Hey, sorry, Chandra, do you have a question?
Yeah, I was going to ask, for the environmental conditions and like water quality, was there any interaction between those and the prey resources themselves? I know you were looking at the potential interaction on juvenile salmon and their bioenergetics, but is there an interaction between some of those and the prey themselves and the prey items that you sampled?
Yeah, so I didn't show that here, but another thing, because we collect information on the prey and the primary producers, I can actually do that same analysis to see what the chironomids and amphipods are eating, for example. And so that has been interesting. Trying to think now, I did a bunch of different runs on that. I think the primary thing that came out of that was that there was a lot of consumption of periphyton. There wasn't a lot of difference between live and dead vegetation. But those are things we can look to what vegetation is actually fueling the prey, which I think is super interesting. We have enough data to actually show some seasonal differences in the isotopic signatures of reed canary grass, because we have a lot of that particular item. So that's always the thing, is you have to get enough examples of the sources to be able to look for those kinds of patterns, but they change over the season. We also have isotopes of water, nitrate isotopes of water. And when I was looking at some of those data, they're influenced by a lot of things, but you can even use that method to identify like sewage inputs and things, which in the Columbia we don't expect to see a lot of. But there were a couple of samples where I was like, okay, this seems like, so in terms of thinking about whether you might be seeing any emerging contaminants or things like that that might influence fish biology, like you could potentially use that analysis rather than doing a complex multi-chemical kind of thing. That was a very long-winded answer to your question. We can get information about the prey, which I think is just as important because that really does tell you what type of vegetation or primary production is fueling the whole thing. So I didn't show that today, but that's definitely in the mix.
Great. Thanks. If no questions in the room, I'm going to hold the last two presentations. I'm going to insert the break now because just based on what's going on here in the room, people are getting a little antsy, and that's a lot of presentations so far. So, and we're also running a little bit late, so I'm going to keep the break at 5 minutes. Our clock says it's 11:08, so let's try to get back at like 11:14. And then we'll do the last two presentations. And again, it's really important to have these question and answers as we go, because it's really important for you all to understand what all is available data-wise to answer these questions. So then we'll have the last two presentations, and then we'll have a discussion about the recommendations and what do you all think, that kind of thing. So come back at 11:14. All right. Thanks, everybody.
Catherine?
come back, everybody. Short break. Yep. Oh. Kind of important to Jeff. Next presentation. Hey,
Hi,
Jeff.
Catherine. Yeah.
Hey, everything
Hi,
okay?
Just, having some issues, but I'm working through them.
Okay. Can you share your screen? Do you want to, or?
I'm trying to here.
Okay.
Yeah.
So see you later much.
Oh, sorry about that, Jeff.
Oh, that's okay. That's nobody's fault.
Yeah. Right.
Oh, there we go. We got it.
Does that work? Or
Yes.
can everybody see
Yeah, we can see it. Thanks, Jeff. Folks on Teams, can you?
I'm sorry, I
Can you see
didn't
Jeff's
get my
screen? Okay. Yeah, it's working. Brad. Folks on Teams, can you see it?
Yeah, we can see it. Jeffrey,
Yep.
do you want to put it in slideshow mode?
Sure.
Yeah.
Is that better?
Yeah, we can see it.
But not in slide.
If you go up to slideshow up at the top of your screen. Okay, yeah, that should work right there.
Does this work?
It didn't work.
It
Try
doesn't
again.
work. Okay.
Hit that, yeah. Oh, there you go. So, it should work. It's just taking, I think it's just taking a second. Or
You
not.
might have to share a different window.
Yeah, you sharing a we were right.
Well, you want to just go? Can you all see it okay on Teams? I know it's a little bit smaller, but.
Hold on a second. I can't see anything.
When you go to your share, did you share the screen? Or did you share no, up at the top? Oh, good. Not that one, Jeff. Jeff, all the way up at the top by the, the leave, the red leave button?
Yep.
Just
That's
go up
what
a little bit there.
Yep, that's what I did.
Yeah,
You
can
want
you
me to start?
unshare it and then try sharing it again, and then this time hit screen?
Okay.
It's a learning process. All right, let's just do the. Okay, just go up to slideshow. If you keep going to your right, hit, nope, no, not that one. Just hit slideshow. Nobody knows.
Can you share your screen or show them?
Yeah.
For the presentation.
No, we're still just seeing the.
Let's just go, you guys. We're running late. So if you want to go up to slideshow at the top of your screen where you see transitions, animations, review, in between that is slideshow.
Yeah, I know that. I know
Okay.
that. It's just not working.
Yeah. Well, it could, okay. If you go to share, hit share screen, you should get two options, share screen or share window. Try share screen. Is that right?
Okay. Okay. Yep.
Okay.
Try this. Is that better?
Yeah, that's perfect. That works.
Okay.
Thank you, Joe.
No, thank you. Thank you for the help. I apologize.
No worries.
Used to in-person stuff.
Yeah.
So yeah, are everybody back and ready to go?
Yep, thank you.
Okay, sounds good. We'll get started. Once again, thanks everybody for being here. I'm going to talk about the fish today, which I'm sure everybody's excited to hear about. Before I get started, I just want to, this project's been going on for quite a while. From the NOAA side, from 2008 when we started doing sampling, and so there's been a lot of people on this project over the years collecting this data. So I just want to give them a big, thanks for helping do all this. We definitely wouldn't be here today with everybody's help. This is a sometimes pretty intensive sampling. A lot of days in the rain and wind and a little bit of everything. So yeah, but it's always very exciting. So we'll move on to, let's see here. Move to the next slide. Is anybody seeing the next slide, or let's see here? I'm not sure how to.
Not yet. Can you see it on your screen? Oh, there you go. Yeah, perfect. Thank you.
I'm sorry. Sorry for all the difficulties. Just, oops, go back. Okay. All right, here we go. Sorry about all this. So everybody's done a great job talking about kind of setting up for me and Curtis to talk about, some of the things that we want to talk about as far as some of the trends and some of the things that we've been seeing. Today, we're going to talk about condition and growth. I do have, we do have the ability to give some pretty good answers to some of the other questions that the ERDIC's uncertainty document had regarding question 5 and 6 with are there salmon in restored sites? And hopefully we'll be able to talk about that at the December 13th meeting. We have a lot of great information about that, but today going forward, just going to talk about the EMP data and kind of how it goes with our growth and condition. So this is a lot kind of what I'll try to go over this pretty quick. Joe talked about this. This is Campbell's Slough in the picture here. So just showing the seasonal differences that we can see from 1 month. This is Campbell's Slough in April and then in March. And so you can see, and we don't necessarily even need high water years to see, a large amount of water at these sites. You can see the channel berm isn't very big, so it doesn't take a lot of water to really infiltrate, to go over that whole area. And so that makes sampling difficult at times, and therefore our occurrence, trying to get a quality occurrence, getting occurrence numbers and abundance can be difficult because of the distribution and spread out of the salmon. And so going forward, we know that when we get these high water events, that catchability it can affect our catchability of sub-yearling fall Chinook. But how is the condition of those Chinook affected by these high water events and all these different and the temperature that is associated with high water events, everything that goes with it. So today we're going to kind of take a little snapshot into that. We have lots of data, but we have a little bit of time today, so I'm just going to kind of cherry pick some of the things we've been putting together for the last couple months. So one thing I want to show here is that so the main part here is to look at Chinook condition and river flow. And so as you can see, Joe talked about how we had some high and low and medium water years. So I kind of classified those years. And this is condition with Fulton's index on the y-axis. And one thing to consider, this is Welch and White's combined. The fish that we see at Welch and White are pretty much identical, they are identical. For the years that we've been sampling, the averages in different age or different size brackets are less than a millimeter. So we combined the Welch and White's physical fish fall Chinook data to kind of strengthen this data set here. The star is on 2012, just because that indicates the year that Welch came on. White's was started in I think 09 and has moved, but 2012 is when we added Welch. So as you see here, we do see some variation in the condition of the Chinook based on the flow.
Hey, Jeff.
Yes.
Sorry to interrupt. I think they said the big group in person, their teams just crashed and there's.
Okay.
Did anyone else?
Yeah, I
Yeah.
think they want you to hang on a sec while they get it back going.
Yeah,
Sounds
Catherine
good.
just, yeah, their team's crashed.
Sorry.
Everyone's having tech difficulties.
Thanks, Carrie, for the
Yep.
heads up.
Hey, Jeff, this is Amy
Yeah.
Bordy. I'm wondering
Yeah.
if while we're waiting, if you could just give a brief statement about what you mean by condition, what that
Sure.
includes.
Sure, we're using Fulton's condition. So that is the weight divided by the length squared. It's a standard condition indice used traditionally in hatchery programs. There's always been a concern that it might, it's not as accurate as it needs to be. However, I think for Chinook, it's pretty much on the money because where Fulton's kind of falls apart is when you have fusiform fish like bluegills and crappies that grow more with length over time, where the Chinook is kind of equal length and width, and that's where the Fulton's does the best job of overall condition. And I can explain a little. It's a ratio, and so you try to be around that number, that one. However, you know, anything above what we see here is anything. All these fish here are just fine as far as condition wise goes. When you dip below like 0.8 is when you need to start concerning that the condition could be kind of going down poor. But although they may still be in good condition, if they're below 1, it just might indicate that they could be more acceptable to stress, I guess. So, yep.
Thank you.
You bet.
Jeff,
Sorry about that, Jeff.
oh,
Yeah.
they're back. Never mind.
No problem. Are you back, Catherine?
Yeah, sorry about that. Teams just crashed on us. Sorry about that. Hopefully we didn't mess you up too much.
No, I think I started the trend of that, so that's on me. So, okay, so I think I'll just keep going on the condition here. We use Fulton's condition indices for this, and all the fish that you're seeing here, despite some variation, they all seem to be in fairly good condition. Anything above, 8 is still pretty good condition. However, anything below 1, you can kind of see that, could be acceptable to stress. You could be in good condition, but if you throw on other variables, you could see, that condition decrease potentially over time. And we see that actually during low water temperatures, low flows, we see that the condition is actually a little higher, which kind of makes sense because the temperatures will be closer to that optimum rate. And honestly, the optimum rate for sub-yearling Chinook for growth is actually closer to 20. It's like 20.34. And that was from Plum and Moffitt's bioenergetics paper that they did. As you see, also the high water years, we see kind of the dipping a little bit below the average. So that blue line is our average condition over all of the years. So it's interesting that it does have some, it does have a little bit of a parallel with the flow. Temperature, of course, can affect this, as well as fish community abundance. Because we only sample at these sites once a year or once a month, we can't get real good, abundance data or occurrence because you saw all the, you saw the drastic differences in water level sometimes, making sampling very difficult. But overall, I will say in 2018, we had a high water year. We did catch a lot of fish that year as well, so the abundance was high. On these lower sites, which is Welch and White, all these fish are from the West Cascade Fall stock, so the lower river wild fish. And generally the fish communities down in this area are fairly low, like we just catch Chinook and sticklebacks for the most part. And so that's kind of one thing you might want to remember going forward. And I just want to this is just kind of to make sure everybody knows where we're at. And so the main thing is, so Welch and White sites, that's where we're getting pretty much all of these West Cascade Falls wild fish. And then Campbell and Franz, because of some of the difficulty sampling, we get more of a mixed bag. And we also get a lot more of the Bonneville Power hatchery fish, which is also known as the Spring Creek group fish as well. We also get, upper Snake River fish. We get upper Columbia fish as well in the Campbell's and Franz sites, but in the Welch and White, we predominantly, the vast majority of our data set is made up of West Cascade Falls wild fish. And so this kind of piggybacks the graph about the conditions. One thing, so if you look, first of all, we'll talk about the pictures. One thing I think we need to realize is that these fish are small when we're getting them right. We're getting in between like 28 and 35 millimeters in March. So these are pretty darn small fish in the system. And Welch and White aren't sites that are necessarily tucked away very much. They're kind of right on the main stem of the Columbia. So these are pretty small fish that are, in the main stem right away. And so we see that in February, these fish's condition is much lower than in June. And one of the maybe concerns is some of the high water years that we see, like 17 and 18, when we have freshets that occur very early in April, that potentially we could see maybe some of these fish getting pushed out to the ocean and maybe didn't go through the proper, diet shifts that needed to be able to, make these shifts that they need to once they get to the ocean as far as food availability goes for them. And so this just kind of shows the progression, like if they can kind of stay in the system, they seem to be, in better condition later on. And then this just kind of reiterates some the differences that we see kind of a little bit in temperature, but also, Lori Wykamp did a great paper in 2015 with a bunch of folks from NOAA that looked at the different stocks and timings. And one big thing out of that paper was that it's necessary to consider the stock-specific variation in life history traits to understand like salmon ecology and survival across all life history models. And so we have Welch on the top and Campbell on the bottom. There's April on the left and June on the right. The main thing you have to focus here is just the big numbers in the middle. So our average fork length in the month of April in Welch is quite a bit smaller than what we'll see in Campbell. This is wild fish as well. And same thing in June, we see that all the way through. So this is kind of a big meat and potatoes slide here. So first of all, we'll say this is Welch and White's Island. This is again West Cascade Fall stock, and this is growth rate, 7/8 growth rate. So you're looking at millimeters per day of growth. And so first, we also tried to look at correlation with flow and growth. Paul Chitterow did this with earlier data and found that really there seemed to be no real correlation with growth and flow. However, we have more years, we have more of this, year classification stuff. So we kind of want to look at this again. It doesn't appear that we see much correlation with flow and growth rates. But I want to point out is so in Paul's paper and for many other papers, it's pointed out that this lower river stock, this West Cascade Fall stock, has had quite slow growth rates below, averaging around 0.55, we get as high as about 0.65. And if you look at literature, so the first two on the left are growth rate ranges. They saw growth ranges from about 0.75 all the way up to about 1.3 in in fish that were collected in the ocean that had been in there about a month. The same thing with the Claiborne one. That was fish that had just been in the ocean. And so we see, and again, looking at the upper river, Snake River fish from a number of studies, we show that they also had higher growth rates upriver on the Snake River fish. So we think there's a lot of growth potential in these West Cascade Fall stock, but as you see, they seem to kind of be underperforming some of the other what we're seeing in other literature. And then, although we don't have a lot of them, the Campbell Slough, we did get some Snake River fall fish, and we saw that their growth rates at Campbell Slough were 0.7. And same thing with some of the upper Columbia River fall stocks, summer fall stocks. They had a higher growth rate as well. And so that also points to some of the, some of the stuff that Lori had pointed out in a previous paper about how the stock specific variation can change. But so yeah, moving forward is kind of a summary. So despite overall fair, good condition, the growth kind of remains slow for West Cascade Fall stock fish. Chinook condition improves with time. However, it may be affected by early freshets. That's something I would really like to, we could also model that very well with the bioenergetics. Because if they're not getting a high energetic, if the high energetic prey doesn't come till a little later, we can model that. We can model different temperature regimes. So there's a lot we could do with that. And growth rates potential for West Cascade Fall stock, that's I think really there. So is it prey selectivity? Is it a high metabolic costs? These are all things that we hope to kind of look into with the bioenergetics model. And one reason we're, so why do we care? We always emphasize, and we do, of course, care about, all the stocks, all the fall stocks, and particularly emphasis on the, Snake River stock. But I think focusing on all stocks, we might be able to, help and identify barriers and things that we can push through or roadblocks that we see from other stocks, just focusing in on, one or specific. They may, be able to be translated throughout different stocks. But one emphasis that I have, or one thing about the lower river Thule stocks here, this West Cascade Fall stock, is that at least from the, from the adult to recreational side, ODFW, WDFW management, the lower river stocks have really have the fall fishery. Not so much this year, but the 3 years before that, it wasn't the fall, it wasn't the upper river brights that were limiting the fishery. It was that lower river Thule, that lower river wild fish. And as you see, over the last few years, they're getting less than 10,000 of these fish back. And that's quite a bit lower than their 10-year average. At the same time, the lower river hatchery fish are actually doing okay. And so, there's been a decent amount of work on this. I know, I think OSU had a grad study that spent quite a bit of time trying to have anglers identify Thule stock to limit, the take, to shut that fishery down sooner. So they were trying to find identification markers of Thules, but that really wasn't successful. So there has been an increased amount of work done on this lower stock fish, as well as all the other stocks. And I guess what I kind of want to take home with this is that for our current goals, which is, this is just very broad, of hoping to get, more adult salmon back, or more salmon back to the Columbia River. And that is just important to understand what level of performance is physiologically possible in order to evaluate the effectiveness of monitoring and restoration efforts targeting this early stage. And so if we can kind of, tune in a little bit with, because we have great, diet data, we have known temperature data, and so we can do these models and compare them with actually known information. And so that, I think, gives us the upper hand moving forward and trying to identify some of these limitations. So I guess with that, I'll take any questions that you might have.
Hey Jeff, I think it's like 20 till noon, so I think I'm gonna move on to Curtis, because we're running a little bit between all the IT glitches that we just both had. Curtis, are you available? Are you ready? And then we can have, hopefully we'll have a little bit of time for a question and answer at the end. And if anybody has any questions for you, Jeff, they can do so at that point.
Okay.
Thanks, Jeff. Really appreciate it.
Yep.
Okay, I am ready, but I don't know if my computer is, so give me a sec.
Okay. Hey, I think,
yeah.
Jeff, you might still be sharing your screen. Do you know how to stop sharing? Yeah, perfect. Thanks.
Okay, my turn to flounder here. Let's see. Share screen. Okay, it says screen, window, or tab. Which was the one?
Screen.
Window or tab? Screen.
Screen.
Screen. Okay. Ooh, where are you? Oh, that's a tab. Nope. Screen. Yes. Share. Can you see that?
Hang on. Yes.
All right.
Perfect. Thank you, Curtis.
Okay, guys. Well, I have to say, thanks to my colleagues for some really great talks showing the breadth of our time series data. And I think it's worth emphasizing the importance of having these long trends in data that we can go back and discern interactions. And that is like the goal of this modeling effort that we're proposing to do. I'm going to say right off that I'm not a modeler, and this is not really a modeling talk. It's going to be more of a conceptual talk about some of the interactions that we can see in the data and what we can hope to use energetic models to extract. Some of the issues from the talks to me are that we have a bunch of pretty complex habitats with a lot of spatial and temporal variation in many of the variables. Especially interannual and within year physical forcings are very variable across years. We see variability in the prey quality in the diets and in the other samples. We see the fish are using the sites, but their growth perhaps is low, and maybe there's some discharge element to their condition that we see. We can expect that climate changes are going to occur, and some of our data fits parameters that look like they could be our future world. So the data that we have, we can use to kind of think about how these systems work and how they might change. Okay, so here's a conceptual model of one way we can approach this, which is taking a bottom-up approach with physical forcings, mainly temperature and inundation, as driving forces for juvenile salmon growth, but also wetland prey and productivity. So both these physical forcings affect salmon and their food. And obviously temperature directly affects salmon metabolism. And this is one way we definitely can use that as input for a model. But also inundation, in that the salmon have access to different areas of the marsh when there's higher or lower water. So there's sometimes opportunity, sometimes there is not. Ian's data from the tidal simulations was really great to show how that happens on tidal cycles, which I'll get into in a minute. But also there's the flood and drought years that Joe showed, which was integrated over time periods. But the temperature and inundation also affect wetlands, in that both the growth of vegetation and the insects that are associated with the different habitats in there especially. This is one area where I don't think we have a lot of great handle on the data, but we can imagine that variations in the temperature regime and in the inundation will affect the ability of the plants to grow, and also the insects associated with them. So there's international variability in all those things. And it's the prey that is the kind of the direct link between what happens in the wetland and salmon growth. So are there timing mismatches? Are there spatial access issues? Those are things that we can look at with models. Oops. So back to the actual prey, which I think is a crucial element here. And Carrie talked about this very well, but I just wanted to point out a couple of things. This is from our flux paper and energy density. So this kind of shows some of the variation across the phylum for different species, as Carrie pointed out. But also, we have to recognize that these groups are associated with different habitats. All the ones I have in orange here are mainly, aquatic or benthic. So they're not in the marshes. They're basically in the channels and water column itself. These other ones, which are the insects, mostly insects and other things, are more associated with the wetlands and riparian zones and other areas. And if you look at the energy content and the other major idea about this is the energy density, but the energy content, which is the weight times its energy. So each individual, prey is worth more than the others depending on how much energy and how big it is. And that varies a lot too between the different groups. So they come from different areas and they're worth more in some cases than others. They have a different prey quality. And the other thing that's important to think about is the abundance of these different things. So for instance, we have a little midge, which they are so abundant, they eat a lot of them, but it's actually a very low energy content. It's small, it doesn't have much energy, versus an aphid, which is exactly the same size, but it's got 3 times as much energy. So that one is quite a bit more valuable to a fish individually. But there's far more of the midges than there are of the aphids. So there's a balance between energy supply and access by fish and prey. So let's just conceptualize that a little more and think about, we have these varying topographies, which Ian showed really well with flooding and emptying. This controls the vegetation community and affects the prey quality and abundance, especially because of access. And, we can think of inundation on the tidal scale. And so in some areas like downriver, it's very tidal. Upriver, Campbell, and everything, those are way less tidal, more river dominated. So our spatial scale of our sites varies between tidal pumping and far less and more riverine effects. So all that's important. But then on top of the tidal stuff is the river discharge, which has big changes over the year. So we've got this, here's a cross section of a marsh with channels, high marsh, low marsh, scrub, and riparian zones. Here's the tidal zone over here. We can imagine then or hypothesize a very prey resource, depending on where these insects and different creatures is their habitat. And this on a scale of decreasing inundation as you go up. So a lot more, obviously, access here than here. And here we can just take a low water, tidal signal, and you have to realize that almost all these channels de-water every tide. So the fish are not in there all the time, and they're coming in, they're using the resource, they're going out again. They're not actually staying within the system all along. And that's really important to realize, like the fish that we're measuring aren't in there for months at a time or anything. They're using the habitats as they move down sequentially. I like to think of these as like feeding stations, opportunities for fish to come down, get food, and leave. But let's take another aspect of the tidal cycle just to think about where these prey are. And here we see a neap tide signal where the water comes up, but it doesn't really go above the bank. It's below bank, which means that only the channels are full of water. So during these times of the tidal cycle, the fish are basically getting benthic creatures, amphipods and the midges and other things that might drop in from or use the low marsh areas. They can't access the higher areas, so they're not getting any of that. Here's these little signals show benthic and aquatic stuff, plankton prey, amphipods, chromatids. These are basically low quality prey. They don't have a lot of energy compared to the other ones, but there's a lot of them. And then we have the terrestrial fallout from some of these things or their access or are associated with the marsh vegetation. So they'll think about the high tide, then of course now they can come all the way in, and there's a much varied, larger spatial scale and potentially a wider range of prey that they can access, including things that are falling out of the trees, which are often big and high energy, very good quality spiders and stuff like that that are dropping off and are being accessed by the fish. So we have this, you know, the overbank access allows increased spatial access, but and also increase the prey availability and potentially higher quality prey. So these prey variations in time and space maybe are a limiting factor or not. Maybe we can see, but that's one thing that we can model as we move along. And just to put it together for the drought periods, it's kind of a similar idea that integrated over weeks, you know, if there's a drought, there's probably less overbank flow and maybe limited access to these higher energy sources, and maybe a higher propensity for the fish to be eating, you know, lower quality thing like phytosterins, which is what we've seen in some of the diet data. There's years where they're eating mostly those. I don't know if those are drought years or not, but that would be cool if they were. Flood periods, again, they have an extended period of time, but one must remember that when the marshes are flooded for extended periods, the terrestrial insects that are associated with a lot of those emergent marshes and things don't do so well. So they're actually, we've seen this in our flux study, there was the flood year had far less of these you know, marsh-related insects coming out because they were drowned. And I think the overall vegetation and productivity is also, you know, curtailed to some extent when there's a lot of water standing on the marsh for extended periods of time. So the floods may not actually be that good for, even though the fish can get into these areas, it could be that the productivity of the marsh is decreased when there's floods, especially for their food. So those are just some of the unknowns that we have that we can actually look at it in some of the models. And here's just kind of a hypothesis matrix that we can throw up, looking at, you know, what should we expect from various levels of inundation? And now I'm talking about drought, flood, average years, and over the course of years that also vary with temperature ranges, low, average, and high. So these are data that we have that we can use to, you know, propel a model forward. And we can look at production of prey as both quantity and quality. So how much of the good stuff is there? How much of the bad stuff is there? What are they eating in propensity, you know? And then the fish metabolism. So up here, so I'm thinking here is like prey, the lower one is metabolism. And we have to think of both of these together in terms of what's the growth potential for the crabs. So that's what we would vary both of these and be able to do some kind of model, a predictive model. And just, you know, for the temperature was pretty easy to kind of think about how a fish might respond, because they're ectotherms, and if you raise the average temperature, they're going to need more energy to maintain that same metabolism as if it was colder. So all these little arrows showing change, average, they would, you know, that's the average growth rate, whatever. And we'd expect the metabolism to increase at higher temperature, but that doesn't mean the growth rate will increase depending on their energy intake and if they can get high quality food to meet their increased metabolic needs. So so here's a little matrix. There's a lot of question marks, and those are related to, because we don't really know how the insect and the prey field changes under these conditions necessarily. I think this is what we are going to be modeling to try to see what we can see from a model, compare that to our real data to make some hypotheses or generalizations at least. So that's our kind of push for building some kind of bioenergetic models to look at some of these variables. I'm not a modeler, and I think we would like to have an invitation to the group and other people to help us work through some of these issues, and especially the form of the model. I mean, in general, you know, we can use the Wisconsin model, which this is based on, and, you know, growth equals the food you eat versus the stuff you need to live and the stuff you can't digest, basically. So it's pretty simple. And the output is our growth rates, size at date, which compare our data, condition, we compare these model outputs to our data. The levers that we can vary are prey energy content and temperature scenarios, like in that matrix. So, but there's other models that are great, like Davis et al. Just came up with one, which was really spatially explicit. That was super cool because they actually looked at different areas of their wetlands and decided that these are areas where this much production would be. So if fish could get there, it would gain those. And they modeled individual fish behavior on like an hourly basis, I think, which is crazy. But it turns out that yes, when they can get up into high energy food areas, they do better. And also eelgrass was a great benefit. But so a spatial model like that, which is way beyond my ability to do, would be super interesting. And I think we have spatial data to allow us to, pursue that kind of thing if we wanted to go down that route. But the Wisconsin model is a simple one. We can actually start there and actually get some results pretty quickly, I think, with some scenario testing there. So potential objectives then is like try to develop some bioenergetic models to look at these output variables given our temperature scenarios that we know and what we might expect in the future. So that would be a climate change objective. What do we think might happen and how we can tweak the model to simulate those conditions. And then, is there anything we can do about these things anyway? I mean, is there restoration designs, construction methods? Do we want certain plants to be there for the future? I mean, thinking about how do we go forward and what's going to happen? Do we want to start planting trees now, or what do we do? What can we do? Those kind of issues, I think we need to start at least coming up and deciding if it's reasonable or not to even go down that route. And then, of course, a lot of these models show you where you don't have enough data and what could be used, what should we do to fill that gap and answer some of the questions. So focus studies then for more experiments, more measurements. Okay, I think I'll stop there. We might have time for some questions.
Yep. Any questions for Curtis? That was a lot.
I'm not a modeler.
Yeah. But I mean, the hypothesis or the intent, the approach of using hypothesis-driven ways of like using these data to try to tweak like scenarios on inundation temperature, and then how would that affect fish? Do we care that the water temperature is increasing? That kind of thing. So this would allow us to do that. What do you all think? There's somebody, sorry. Chanda, sorry.
Curtis is showing. I think Curtis is sharing screen.
Hey, Curtis, do you want to stop sharing your screen?
Oh, yeah, okay.
Awesome.
I thank you for that presentation, Curtis. I thought it was really helpful, and I liked the hypothesis framework and thinking about, in general, even in that large suite of questions that Catherine shared at the beginning, kind of as we go into SM3 and thinking about what can we do and how is it going to address specific uncertainties. Some of the results from your presentation that I thought was really helpful in context of a site and looking at site scale versus larger landscape scale principles when we think about like connectivity. And we typically think high water, more connectivity is great because fish have access to more areas. But I thought that what you presented and looking at what prey are actually available and how long things are flooded actually has implications for that export question and prey dynamics. And so I'm happy to see this next phase of work that you're going to be doing in terms of building on the prey export study that you did a few years ago. So those are some of my initial thoughts, in seeing this presentation, and all of them, and looking at each of the people that have presented today and how you all see your research in the context of those broader questions. It almost seems like we need a weight of evidence kind of graph saying how confident we are that we know the answers, or at least something about those big questions at the beginning. And then that might help us to target and figure out what additional monitoring and how can we complement the work that's already been done. Over.
Great, thanks, Jana. Curtis, any kind of response, or is that, I think I've got a list of things that she said that I will summarize.
Well, I appreciate that. And I really like the weight of evidence kind of idea, because it's hard to actually disprove a lot of things, even though that's what we try to do with hypotheses. So yeah, how far are we? What's the weight of evidence for all these topics? I think that's a great idea.
Awesome. Hey, Chris.
Hey, how's it going? Just kind of interesting, your kind of discussion about, match and mismatch, especially as we're moving forward, is there, do you see kind of a, maybe it's a worst case scenario, but a best case scenario in terms of, prey abundance, for a mismatch, especially considering, sea level rise, warming temperatures, essentially trying to find a win for everybody, in terms of prey, right? So maybe some of the habitat restoration should be focused on potentially lower energy prey because it's more available to more things that are eating it, trying to find a win in the weeds, I guess, right? Does that make sense?
Yeah, just thinking about the scenarios, it would seem like an early flood would not be great because it would cut down a lot of the higher energy insect growth, is what I'm kind of hypothesizing about. But they do eat, the thing is that, as we've seen, their diets are full, they're eating a lot of stuff. So there's not like a lack of like food for them. It's now, I think it's more the quality is kind of an issue. Like if you eat just if you don't have to work so hard to get high energy food, that seems like it would be an advantage. If you eat a lot of high energy food and your stomach's full of that, maybe you'll grow faster. If your guts are always full of daphnia, which are basically water drops, I think you're going to, you're working hard to get all those little bits of energy. So I think there is a quality issue, but I don't know how well it's quantified in terms of growth rates. Maybe the aquaculture literature has got some interesting, aspects about that, but it just seems to me that, and this is one thing we can do with the I guess the Wisconsin model, at least you can put in just low calorie diets and see how fast they grow at a given temperature versus other ones. So something that could be played with, and yeah. I think the scenarios are interesting, and maybe it'd be fun to come up with a list of realistic ones and what are their potential impacts on fish growth.
Thanks. Thanks, you too. Amy, did you have a question?
I think April was first.
Okay. Hey, April, sorry.
Oh, no worries. So it seems like maybe there's at least potential, if not intent, behind this to inform project design. Because so much of the work we do is manipulating elevation and vegetation. And I know there's, the factors such as temperature we can't manipulate, but it seems like it could be really valuable for informing project design and having different elevations and looking at specific sites in proximity to one another and adjusting elevation so that we give a range of habitats if we can really dial in. I know it's probably different by river reach, but this seems like really valuable information to have to kind of inform some of those target elevations in plant communities.
Yeah, agreed. Thanks, April. I think that's one of the questions or one of the objectives is to, like you're saying, dial things in, like the elevations or the connectivity or the elevations of channels kind of thing. So yeah, thanks, April. Amy?
Yeah, I agree, April. That's awesome idea. I guess I just wanted to ask the question about, I think this bioenergetics pathway is great. I think it's a really good goal to try to get a better understanding of that. And I'm wondering, maybe back one step, how you feel about the availability of data to make the predictions between the environmental conditions and the plant detritus, community and prey availability, and if that is another step that needs to happen, or is that already kind of there?
From my point of view, who's on modeler, that seems like another big step that it would, of course, it's of interest because it's driving the prey populations, which is a big unknown. So I would love to add something like that, but I think the first cut is, I mean, I think we should go simple first, basically, and just see what we can find out by only using a few levers. And every time you have another lever, another trophic level that you're working on in there, it's, you know, the uncertainty blows up. So my personal view would be to keep it as simple as possible first and expand once we have some generalized answers and then get more specific. But obviously, what's driving the insect population? Yeah, it's like what they eat. And yeah.
Any other questions? All right. We are doing an abbreviated series of presentations for the annual ERDIG meeting, so you'll hear this again. And I have captured a series of questions for follow-up. And please let me know where I'm wrong or add things to this list. So I have the utility of Tableau and or other ways of sharing data and making data accessible and usable for other folks, including decision makers, but for restoration design and or evaluating restoration projects. So how do we do a better job of using the data that are coming out of these programs and sharing the data and making them accessible and usable for folks? So that's number one. Number two was looking at climate projections and changes to accessibility and temperature. So looking at the climate projections with habitat access, so structural information, but also the bioenergetics. So the quality of habitats. So the bioenergetics modeling is to look at these different levers of temperature and inundation and prey and how that affects salmon growth. So there's that. Number three is salinity changes. I think Jen Morris pointed to this, and whether the intrusion into the lower river and how it will impact vegetation communities, possibly prey as well. Number four, Shannon's idea about the weight of evidence. So which questions do we feel like we can answer pretty well as of now? And then which questions still have a lot of uncertainty and we need to continue monitoring and doing more applied research. And then the end-all question about prey associated with wetlands and what we know and what we probably need to do some more research and or monitoring about how prey changes with vegetation and wetland conditions, inundation, and timing. So am I missing anything that folks have pointed out? Did I capture that pretty well? Okay, well, if you're interested and you want a follow-up, please shoot me some more questions and we will be sure to kind of continue this conversation at future science work groups and science forum meetings. But thanks everybody, that was a lot of information. If you want to just hang out and talk a little bit, that's great. Otherwise, folks, we'll be doing abbreviated presentations like this at the annual ERDIG meeting in December. I think it's December 13th that Jason pointed out. Okay. And if you all want to stay on, have at it. But thanks, everybody. Appreciate it.
Thanks a lot. Good job.
Thanks all.
Thanks, guys.
Yes,
Thanks, everybody. Don't
Thank
let things stress you out. I know today is an
Too late.
auspicious day.
Too late, Catherine.
An auspicious day.
Catherine, today's my birthday. It's a great day.
Hey, Mark, do happy birthday.
It sounds like it's my birthday. It's a good day, y'all.
Thanks, Joe.
You should have had everyone on Teams.
Yeah, oh, yeah.
I didn't want to bring attention to it. I felt like I was bringing attention to it, not
Thank you. Oh, man.
What do you, anybody want